Morning students. In this video I'm going to show you how to draw the vector sum of the electric field vectors from two charged objects at a point. On the AP exam it's rare for them to ask you to, I'm not sure I've ever seen them ask you to draw the electric field vector from more than two charged objects at a point, but this is a relatively common task. So on the left, I've got a large version of the diagram. I'm going to work on this one over here, and then we'll just draw our answer vector over here. So there's a 2 nanocoulomb charge, 2 times 10 to the negative 9th coulombs, at a distance of 5 centimeters from our point of interest here. And there's a negative 1 nanocoulomb charge at a distance of 4 centimeters from here. So the first thing probably to do is to think about the behavior. This is a positive charge. So at this point, if I put a tiny test charge here, a test charge is always positive, it would feel pushed away from that positive 2 nanocoulomb charged object like that. And it would feel attracted to this negative 1 nanocoulomb charged object. So the individual vectors would be in those directions. Now the next thing probably to do is to figure out the relative length. We're just doing a qualitative determination. We don't need to calculate exactly how long the vectors are, but it'd be good to have an idea of how long they are relative to each other. So remember that Coulomb's law for electric fields is derived from Coulomb's law for electric forces. That's kq1 q2 over r squared, or 1 over 4 pi epsilon naught for k is also equivalent, but E is F over Q, so that we write that's equivalent to kq over r squared for an individual charged object. So I don't need to calculate that again. I can just think about it. This would be 2 over 5 squared, approximately, or relatively. And this, the electric field vector, perhaps I should write that over here. The length of this would be proportional to 2 over 5 squared, and the length of this vector would be proportional to 1 over 4 squared. So that's 1/16, and that's 2/25, or 1 over 12.5. So the vector from the 2 nanocoulomb charge, the electric field vector, will be longer. Not a huge amount longer, but slightly longer. So I'm going to erase this stuff. I know which one is longer now. And I'm going to redraw the vectors maybe a little more carefully. This has to be in a line there, longer than this. Probably best to label them in some way, like 1 and 2 or A and B. So this is EA and this is EB. Now the vector sum is often given by a tip-to-tail diagram, so that's how I'll do that. I can move this vector over to here and draw the same vector at the tip of EA. So that would be drawing a shorter vector over here that represents EB. Oh, and yeah, it's real typical to give these a little vector symbol. So the vector sum, is going to be here. And this would be EA plus EB in vector notation, or the resultant vector. Should angle up slightly. Well, I don't know for sure. I could probably, if the question was quantitative, I would calculate what the vertical component of EA is. But I'm just sort of working here as a guess, and I'm just going to say that EB is a little shorter than the vertical component of EA. Perhaps I should check that, but for the purposes of this video, I'm not going to. So then what would we draw? Well, over here, we draw a vector that looks something like that, if this is the AP exam. And then if they wanted a label, we would label it. Maybe E net, or just E. Either way is fine, I suppose. I hope that's helpful. There are many versions of this kind of task, but it typically does involve just a quick determination of the direction, a guess at the relative lengths, and then a vector sum via tip to tail, or if there's another method you prefer, you can use that. The parallelogram method also works. I might show that in a later video. I hope this is helpful.